Good morning, good evening, good afternoon, depending on where you're joining us in the world. Welcome to the MECI Alliance Seminar Series. Not only am I your host today, but I'll be one of your speakers. I'm joined today by my colleagues, Jose Pacheco and Dave Hart. Collectively, what we'll try to do today is share a little bit of experiences and projects that have been at this intersection between manufacturing and design and computer science and machine learning. And then we have an invitation for you, a desire and a need for your guidance and collaboration. So let me share my slides here and we'll get started. Share screen, continue screen number 1. Okay, very good. So here we go. Hopefully the screen's coming through okay. Just a quick check. Perfect. Yes. Okay, thank you. So an amazing time to be in mechanical engineering in general, but certainly in manufacturing and design. And it's amazing because as a mechanical engineer, you sort of in this current era of the growth of machine learning and AI and sensors, we can continue to do the things that we've been doing, but now amped up on computer science, amped up on machine learning, amped up on sensors. And let's talk a little bit about what we can do and what we've done. So the agenda, a little bit of some recent examples, specifically in the areas of controls in manufacturing and related to design. And then we'll use that as an invitation. Oops, getting some feedback. Not sure what this is. Dave, you maybe getting a preview possibly. I'm not sure. Okay, okay, I think that sounds better. And then an invitation. So let's start. So learn control. So what do we mean by that? When we think about control in a manufacturing setting, we have some control signals that are coming from sensors that are trying to maintain the quality or a set point on a machine that is making a product. And we have sort of data in and material in and data and material out. So the data going in is our control signals. The materials going in are raw materials. And that could be coffee beans or it could be glass rods that go into machines. And those machines could be a draw tower of an optical fiber or a coffee roaster. And the product that comes out is coffee beans or fiber, whether it be for apparel or optics. Right, so working backwards again from the product. Here's coffee. You got to that coffee through some coffee beans. Well, here's some fiber. And you got to that fiber through some extrusion phenomena of some material that had a cross-sectional set of properties. And those materials ran through machines. And that machine was a coffee roasting machine. This is a fiber extrusion machine. Okay? And those machines are complex and they're controlled by signals over time. So pressures or temperatures and gas flows or velocities and forces. Okay? So that's a little of the context. Now, like, how do we then take this as sort of when we're manufacturing, we're trying to make a product, we're trying to design and execute quality production of something that is going to be in the customer's hands. And so you have some kind of process that's making your fiber or making your coffee. And there's some controller that's saying, hey, I'm measuring an aspect of this thing, the diameter of the fiber or the temperature of the coffee, and I want to control it. In this case, looking at the fiber, I want to control the temperature that's being used to melt the preform. I want to control the tension of the fiber. I want to control the diameter of the thing that I'm making. By and large, if you do a sort of a survey of most controllers, programmable logic controllers, and the way that machines are controlled in practice now, they will use PID, proportional integral derivatives controllers that work well and are understandable very mathematically rigorously for linear time invariant systems. And then there are innovations that take us beyond linear time invariant systems that incorporate some models of the process you may be able and maybe wanting to control. But something like a PID controller or for a system such as either coffee roasting or fiber draw or 3D printing, where you want your process to be far more dynamic. And you want your process to be dynamic if your product is dynamic, if the product is changing over time, whether it be in the optical properties or the dimensional properties. Controllers, sort of the PID sort, work really, really well when they're modeled and tuned around a nominal set point. And it's hard to change them for new set points, new operating conditions. And it's hard to completely capture the nonlinear dynamics for systems that include fluid dynamics, heat and mass transfer. So the question that we've been taking with many, I'd say many, about 5 now, industry partners, is, well, let's actually figure out how we can integrate machine learning into real-time control, right? Where we want to, obviously sort of have the performance that a conventional controller would give for you, proportional integral derivative control, making sure that your error is small and you're sort of applying control effort when your error goes large, try to maintain within spec. But how do we then take that process of operating around a set point to learn about the process that we're controlling, to learn about the material that's flowing through, and not have to learn from first principles, but informed by first principles. So let's look at how do we improve controls, where we're looking at things that are hard to model from first principles, but learn a lot more while we're doing the thing that we want to be doing, just producing a high quality product. So the framework, if you think about this for a second, is in this era of data, it's big, and you're getting lots of data in a manufacturing context all the time when you're doing control. So we have control trajectory signals that we're using to control the extrusion rate or the winding rate or the heating rate of fiber or the pressure and temperature of coffee beans that are being roasted. Goes into the machine, interacts with the product. And when we learn to control, we want to learn the physics, learn to optimize, and learn to make new variants of the product that we're making. In the language, this figure, in the language of deep reinforcement learning, looks a little bit like this, right? Where we have some type of action, some type of thing that's interacting with the world, our controller. We have some environment that we're interacting with, in this case, the manufacturing process. We have some type of reward, the control signal that we're trying to minimize. And well, there's potentially now this ability to add something else, this agent, a higher level layer of logic that allows us to improve over time, to not just say, hey, we have our fixed gains, our fixed way of operating, but let's allow us to learn online, not offline, not collecting the data and go sitting in front of your computer connected to Amazon Cloud and doing it at your leisure, but doing the real-time learning while you're real-time controlling. So that figure, right, if we sort of break it down into this sort of architecture of deep reinforcement learning, we have sort of all these little pieces that maybe you've heard about if you've seen some of the literature in machine learning. We have some actor or agent, we have the machine. And there's a measurements being made, the diameter, how fast the fiber is being pulled, how much heat is being put in. We measure the diameter, and we want to minimize the error between the diameter that's being produced and the diameter that we want. And then there's all this other stuff that is sort of what we're wrapping around it, which is the machine learning aspect. But if we drill into this for a moment, let's go piece by piece. This little aspect of this reinforcement learning flow diagram, the blue box here, if we drill into that, is really not a lot more than a conventional controller. We have some reference that we want to control for, the diameter. That goes into a machine, that goes into a controller that's deciding how to apply control effort to our machine. In this case, the motors for extrusion, the motor for spooling, and we measure something coming out of the machine, in this case, the fiber. And we put it back around and we have this controller. So this deep reinforcement learning agent in this little aspect looks a lot like a conventional controller. And we have that piece. That's what allows us to do sort of real-time control for that machine. And then these other pieces are wrapped around it. The machine learning aspect, the ability to learn and observe over time. So we have that controller that's controlling the machine. but we're storing a history of all the data that we've been receiving, both measurements on the machine, measurements on the materials in and out. We have some additional sort of reward, some objective function, and we're still trying to minimize error between what we want and what we get. So that is roughly what the reward functions will look like. And then we have some additional logic, which can look like a neural net with multiple layers, multiple nodes, which is really just a complex way of fitting data to models, learning the models that explain the data, but then help us to inform and guide how our PID gains, or how the gains of a slightly evolved controller may need to be modified to get even better performance. Right? So this, to try to demystify a little bit, in manufacturing and design, we've been doing aspects of machine learning for a long time. Feedback control is machine learning. Statistical process control is machine learning. But now with the advent of additional compute and additional sensors, efficient compute, we can add a lot more compute to happen in real time and learn more about the system as we're controlling it. So a paper that really was led by Song-Woon Kim recently came out that talks about this very notion in the application of controlling fiber. So we started with a lab-based system to make a polymer fiber. We're now collaborating with a optical fiber manufacturer to deploy our learnings onto real draw towers. And what this figure on the left is just denoting is if we did nothing for this integrated deep reinforcement learning with an embedded real-time controller inside of it, if we didn't tell it anything from the very beginning about how the machine worked and how it would sort of, maybe not optimally, but how it could run, over time, it slowly learns. And at some point, depending on your learning rate, starts to reach performance measures that are better than what a PID, an optimally selected PID controller could do for you. And we're in the process now of applying these same learnings to other processes with additional industry partners, in particular, looking at coffee roasting. Now, I didn't say too much about the sort of the fiber draw process, and I had to explain a little bit more to share why this figure is so interesting. If you think about optical fiber draw or extrusion in general, it's a mass flow problem. You're pulling mass out of a heater that's melted the material, and you're pushing mass in. And there's some complex physics that are happening in terms of the heating, the heat and mass transfer, and the neck down of the nozzle that goes from a large area to a smaller area to produce the diameter of the fiber that you want. One of the exciting things about this plot, if you just sort of look at it for a moment, is if I wanted to make if I have a fiber that's being extruded, I wanted to make it go smaller, I just pull faster, or I could push slower. And so one of the sort of the intuition reinforcing things that we see that this controller, that the system allowed us to do, is to simultaneously figure out, well, what's this sort of simultaneous pushing and pulling that appropriately rapidly deals with the transients if we're trying to change the diameter of a fiber over time, and we'll sometimes pull faster and sometimes push slower to accomplish the same target change in the diameter of the fiber that we're trying to produce. So this strategy is something that we're now very excited by and are rinsing and repeating in a number of different processes. It's a strategy that doesn't require a completely developed first principles model. It can be seeded by first principles, but learns over time, learns to deal with some of the difficult and hard to model physics that are embedded in the process that we're controlling. And it's using this notion of deep reinforcement learning, but in real time, right, to sort of really over time make your system better, higher quality, deal with transients in a little bit better of a way. Now, one of the things that we've really interestingly run into, as you can imagine, there's a lot of installed controllers in the world, whether they be for optical fibers or coffee or painting or assembly. How do you approach this wonderful new opportunity of machine learning in real time on existing systems? Where do you even get started? So just to share a little bit about that, and would love to talk with many of you about how to amplify that in your facility or in your research. If you think about a system in some sense, it's a bunch of blocks. We're taught to draw it as blocks in a block diagram that are connected with arrows and feedback loops. Here's a sort of a very rough drawing of the control loop for a fiber draw system, where we have this black box, which includes the furnace, how the material travels, the capstan that's wrapping it up. And then there's some controllers, these red boxes, one controller controlling the tension of the fiber, another one controlling the feed rate of the material going in, another controller controlling the feed rate of the material coming out, right? And so the way that we approach sort of decomposing a sort of existing system is that often, and typically, we'll have data at the inputs and outputs, output ports of all of these boxes, right? So we know what the controller is, so we know what the PLC and what it's doing. It may be a proportional integral derivative controller, and we'll know what it's doing, but we can collect data at the input and the output and look at a regression model to confirm that it really is a P or a PID or a PI controller. And then the more complex thing, though, is to collect the data that's coming out of the controller and into the system for which we don't have a good model, and we develop models for that. And then once we have that model, then we inject it into our control system, where we have a process model that allows us to do feed forward. And that process model can sit outside the PLCs that you're probably using to control your current system. And it can be either sort of an additional laptop or additional computer, or increasingly, certainly, as we think about integrating this in more cost-effective ways, putting some of these functionalities into the next era of programmable logic controllers. So our approach to this, right, is very much, how do we go from data to deploying? We'll start with some intuition for the model of the process that we're trying to control. Targets the type of data, the type of machine learning structures that you may want to use to learn a little bit about it. But we don't just use, it's not just the blind application of a blind regression model. Taking some of the physics, machines we know oscillate in a particular way, heat transfer happens in a particular way. So informing our machine learning with an intuition for the physics, and doing, as we would normally do, designed experiments to collect data. In the manufacturing environment, if you have a lot of bad data, you're probably doing something wrong. So one of the other interesting challenges about machine learning in the manufacturing environment is you have lots of really good examples and fewer bad examples. And so having some physical intuition for what's going on dramatically helps with accelerating your learning and application of innovations in the controller to improve quality. Okay, so the generalized approach that we're taking here is starting with existing controllers, collecting data before and after the process, collecting data before and after the controllers, using machine learning techniques to then develop a process model. And with that process model, we're able to improve the controllers for better set point tracking and better recovery from transients. So let me transition now for a moment. I want to tell you a few quick stories. So that was all about real-time control. Let's take a step back and say there's a lot of interest in industrial Internet of Things, or how we can collect data across our entire enterprise and use it to learn something. Learn when machines are going to be predicting when they're going to be down, or understanding the efficiencies of different arrangements of people and resources. So many individual companies are certainly excited by AI, machine learning, Industry 4.0, the industrial Internet of Things. An opportunity that I think maybe goes beyond that is breaking down the four walls of the factory, making our factory smarter, certainly by collecting data and figuring out how we can extract actionable information from that data inside our four walls. But what if we also, maybe somewhat analogous to learning population data from people for healthcare and wellness applications, what if we share our data, maybe across companies, across collaborators? can we get even more valuable information? And can we develop the business model around which allows us to share data in a safe way? So there's an evolving understanding, sort of a belief that data sharing, beyond just collecting the data, using the data in your four walls, but allowing us to share data along the value chain, along the supply chain, both with your customers and potentially with your competitors, there's dramatic financial opportunity. But you should be, my suspicion, a little suspect by that. I'm not going to share my data. Why would I want to share my data? It's my data, it's my proprietary data, it's my secret sauce. Fair enough, right? But the argument is, and I believe the belief is in many scenarios, if there's some willingness to share, there's additional value, additional benefit. And if we can lock down the pieces of information that's in your data that is your secret sauce, and allow things that aren't your secret sauce, that are maybe more about the maintenance of a machine, or sort of how a particular process that's a general process that's used by many manufacturers is used. So how do we connect, and why do we want to connect our data with others? So David Kang, is a doctoral student in mechanical engineering, is really looking at this area of manufacturing and data sharing, privacy and data and learning. And the concept, if I didn't make it clear, is sort of highlighted here. It's quite simple. If I'm one manufacturer, I may have a little bit of data about a machine or a particular mode of failure, and I would like to use all of my data, sort of label data, good and bad, and figure out, well, what is a decision boundary, a classifier that allows me, with a new observation, to know whether something is good or something is bad. Quite typically, if I'm a good manufacturer, I'm going to have lots of really, really good examples and very few failed examples. So it's going to take me a long time to figure out on my own where this decision boundary may be. But maybe I can aggregate data across, maybe I collect a lot of my own data, or maybe I collect data across multiple sites, or for even bigger data, I will collect data in conjunction with my collaborators and partners. So if we do that, right, if we have multiple data sources all coming in, that gives us more data. It gives us a better ability to make this boundary. Now, the question is, okay, how do I do this in a shared way, in a secure way? And an area where we'd really like to collaborate with you, both in the technology on machine learning, but also the business models for how we may be willingly sharing data. The way that we technologically enable this is through some encryption techniques called homomorphic encryption, where if we can make sure that your data is, when it's shared, it's always protected, but not just protected, that when we do the machine learning is happening in the encrypted space, right? So we don't unencrypt, we don't decrypt the data to do our learning, but we actually use encrypted data and process on the encrypted data. So the techniques that David is developing is allowing us to implement what you would think of as your sort of classic or sort of more modern machine learning techniques, whether they be classification or regression techniques using support vector machines or decision trees, but doing that on the data that's been encrypted. And we believe that that sort of framework is going to allow us to really explore the idea of sharing data across multiple factories, across multiple companies in a way that is both technologically secure and has some really interesting business models associated with, well, if a data breach were to happen, maybe there is an insurance model that an insurance provider can provide to backstop that, but with a known and quantifiable risk portfolio because of the security key that you're able to put on the homomorphic encryption, for example. Just to highlight, there is a paper that David recently put out. It's just coming out now in the Journal of Manufacturing Systems that really talks about this application in the context of machine maintenance, machine service. So collecting data across multiple sites. He implemented the Fourier transform in the encrypted space. Right? So the Fourier transform, well-established algorithm to extract frequency components, but doing that on encrypted data and getting the same result was one of the big innovations for this paper that David recently put out. So this other little story, again, wanted to share with you is sort of thinking about how we foster data sharing across manufacturers to get more value out of your individual data in developing both the technology for doing the sharing and thinking about the working with industry partners to try to articulate the business models that will make sense once the technology is fully developed. Okay, so the last story that I want to tell you, and then sort of I'll try to we'll put this together in sort of a some opportunities for collaboration and some lessons learned. Video-based machine control. If you go into a factory, it's not uncommon to find a camera that is taking images of something coming down the conveyor belt, a circuit board or a car door, or the height of fill of a bottle, and making decisions about the way that that part or product looks. Is the fill high enough? Is the cap on straight? Is the circuit board or the components oriented in the correct way? There are many applications, though, where it's not the single appearance of the object that is indicative of its quality or its health. It's indeed a motion, and how something looks over time. What we're looking at here is a diaper packaging line where material, the diaper, is flowing through a machine, a big printer, think of it, and it's being wrapped. And what we'll notice here is at some point during the video, if it's playing well over Zoom, there's a little bobble in the flow of the material. And that little bobble was actually the glue sticking to the machinery. I'll play that again. And that glue stuck at the beginning, but later on in the machine, it gets stuck a little bit more. And when the clearances get small, it completely jammed. And then when the complete jam happens, if you had to unjam your office printer, you know that can take an hour. If you're unjamming a factory scale printer, it's hundreds of thousands of dollars and lots of hours. And so what you'd like to do is observe how this thing is flowing, how this thing looks, the material looks over time. In this case, happens to be a diaper being packaged, and to use information extracted from the video to stop the machine, adjust the flow rate of the machine, or do something. Now, this is very applicable in scenarios where you don't have a good sensor that is would be able to detect vibration or other signatures. This is something that is an amorphous, flexible, flowing piece of fabric or paper. Now, how do I go from this video to being able to control the machine? How do I go and produce something like this, which is a control loop, where now my sensor is a camera acquiring some video. I have my set point, which is the video of the way that I want the system to look. And I need to compare those in real time. So without a doubt, you can go to the machine learning cookbook of approaches and see that many of them aren't really great at real time. And many of them need lots and lots of big data, lots of examples. So not only do we want to figure out how to compare video clips to control our machinery, but we may want to guide our comparison. The data that we may have as example could be as small as one example. So how do we approach this problem? If I want to control a machine based on the way it looks over time, or the way the material is flowing over time, the approach that Fitriani took in her work is really this concept of what we'll call the video alignment path. If you think of a video as a cube of data, 2 spatial dimensions and 1 temporal dimension, it's a volume of data. And I may have an example of the way that I want this volume, this thing, to look over time. My example, my control, my set point. Here's this trajectory of appearance over time. And then I have new incoming video streams. We've developed an algorithm and an approach that says, well, actually, we can dramatically reduce all this data complexity. These are gigabytes of data per second coming at us in this high-speed streaming video. But we can simplify the problem by saying, let's ask the question, if our video were a Slinky, if you're old enough to remember what a Slinky was, and had your Slinky go down more than 1 stair at a time. But if you think of your video as a Slinky, a sort of a long, stretchable spring that can be stretched locally and compressed, it can be distorted up and down. How do I take my video, one video, and stretch it, warp it, to make it follow the trajectory and path of another? So Fitriani developed a number of both hardware techniques or hardware accelerators for software techniques to do this very thing. So to take two videos in, compare them by asking the question, how do you stretch one video to look like the other? And once I stretch this one video to look like the other, I have a trajectory, a motion path. And from that motion path, now that's a dramatically data reduced thing, a trajectory, from which we can calculate similarity in time or position or appearance and use that to control our system, apply the control logic to adjust our machine to either stop the diaper before it gets, stop the presses, stop the diaper before it jams, or to slow the machine down, for example. And this builds on top of the GPUs that you will use in gaming, a highly parallelized algorithm that takes as input a sensor that is a camera. But in the end, right, all that machinery, if you will, goes to produce these run charts that you see all the time in the practice of manufacturing, of process control, of statistical process control. So in this diaper example, and I'll go to this next slide here. In this diaper example, this is a run chart that where the diaper is being produced very well. There's not a lot of error, deviation in the temporal trajectory of this path, the spatial temporal trajectory of this path. And at cycle N, so that's the first cycle where there's a little bit of a bobble, there is a measurable change in the trajectory of how these two videos are aligned. And so that allows us to sort of flag when something has happened. By the time several cycles later, when complete jam happens, there's dramatic deviation in the spatial similarities, the temporal similarities. And in this way, we've, in a very fast and computationally efficient way, go from videos, these big cubes of data, aligning them in time and space to extract a trajectory that gets us to a number that says, what is that overall similarity? And using that to flag and control, in this case, a diaper packaging process. Okay, so I hope I've excited you. I hope I've sort of alluded that at this intersection between mechanical engineering and the application of instrumentation and sensors and machine learning, there's a huge opportunity. Broadly, yes, we're all engineers, we collect data, but in the area of design and manufacturing, I think it's probably even bigger. I'm biased, but it's bigger than, you know, it's plenty large in that space by itself. So the other thing I want to share with you, and I'll be bringing in Dave and Jose here in a moment, through the MECI Alliance, through mechanical engineering at MIT, we've been reaching out to industry and with our students and alumni to establish better relationships, better community. During COVID, we had a few experiments. Certainly, we initiated this seminar series that you're spending your time today. So thank you. We also had, before COVID started, we had, and still will, have industry immersion projects, which are summer internship opportunities for graduate students, where we've co-designed the activity with industry and MIT faculty. And then more recently, over the last semesters, we had a flavor of UROPS, undergraduate research opportunity projects, or ELOs, enhanced learning opportunities. And we've learned some things. We've learned in our collaborations with industry, there's a lot of interest in this activity and intersection between the physical and the data sciences. There's appetite and an opportunity for engaging with companies in ways that are different than a multi-year research project. Like, we need to start working together. That's something bigger than a class project, smaller than a multi-year research project. And there's an appetite and a need to develop some of those sort of more targeted, more timely, targeted collaboration opportunities. And at the same time, as at MIT broadly, and certainly within the department, you know, we think a lot about the evolution of mechanical engineering in this era of compute and data science. And we believe that simulation modeling, data analytics, so the machine learning framework, is a unique opportunity in design, manufacturing, and robotics broadly for us as a department to engage with industry. So we've been doing some internal questioning. In general, and in the area of data and compute, how do we as researchers collaborate? how do we want to collaborate? How can we better engage with industry and our alumni in education, in our research, and our service? And what should we do as a department, as a faculty, for our investigators and for our students? In asking those questions, we've come up with some themes. It's very helpful to have mechanisms to enable small project opportunities with industry collaborators, and having a vehicle that allows us to do something that sometimes can fit in a class, but a class can be extremely constraining. And something a little bit smaller than what you would do potentially with a 2 to 5 year research project. This also seems to be an opportunity to expand professional degree offerings, so master's programs that are maybe targeted in a particular field. And we have one of those already in the department, the Master of Engineering in Advanced Manufacturing and Design. And certainly looking at continued education. So what we've decided to do as a department to further inform this idea of how do we get some small projects going that could be anything from Europe projects to master's level projects, but are not at a multi-year sort of research project just yet. We've decided to pilot an experiment that is bringing to bear machine learning, data science, but in the context of a degree program that we already have. As I mentioned, we have the Master of Engineering in Advanced Manufacturing and Design degree program, a 1-year professional degree, and Jose and Dave will share a little bit more about that. But what we want to do, starting in September, when the new students come in, is pilot a flavor of projects within that degree program that are heavily biased towards machine learning, data science, in the practice and realization of design and manufacturing, and use that to further inform how we should evolve as a department, how we should evolve in offering 5th year opportunities, or sort of this contextualized machine learning and data science and mechanical engineering. And we continue to get input in working with you to establish these projects and opportunities. So I think with that, Jose, and Dave, I want to turn it over to you. And I guess I'll just continue to click, but I'll start with this slide. Oh, okay, Jose, you want to take it over? Excellent.
I'm going to try. So we'll see if this works. So thank you, everybody. And thank you, Brian, for this great context setting about these pilot projects, because we're quite excited about the educational as well as the practical applications of these data science pilot projects that we're going to be doing. And so now, obviously, if we're going to be educating future engineers in manufacturing and design, it's extremely helpful to be in a factory setting. And so that's why these pilot projects are with host companies. And so I see that I'm not able to go forward.
Yeah, just tell me click and I'll.
Yeah. So go ahead, please, and click the next one. And so first, to give you a little bit of background very quickly about the program, this Master's of Engineering in Advanced Manufacturing and Design that we have is now going on its almost 20th year. It's a program that was designed to educate technical leaders in manufacturing industries very specifically, and allow them to fully participate in taking the concepts that they're learning in the classroom around the technologies, around new products, new processes, how to design supply chain models, and implement them in a real world setting and be able to understand how to do that well. We also, of course, have to think about the general context in which they're practicing. So being able to do that in a socially responsible way, and to be leaders in not only well-established companies, but those companies that are rapidly growing, and when the time is ready for many of them to start their new companies. And so that's the mission of this program. In the next slide, we can see that our approach in educating these future leaders relies entirely on giving them a systems view of manufacturing and providing a strong base in for them to work in industry by emphasizing a math and science-based methods for analyzing, designing, and operating manufacturing enterprises. And you have to do it in a global context. We're not just talking about the US. We also have to think about all the different forces, all the different things that are affecting the manufacturing enterprise around the world. but we need to do it also in a very short amount of time. Many of the students that come to the Master of Engineering program are looking to take this information, understand it, and implement it very quickly. And so they are not here for 24 months or 5 years. They're here for 12 months. And so they're very practically oriented. Now I'll talk a little bit about some of the exceptions, but in order to be able to do that in such a short amount of time, we've broken up the curriculum into 4 different areas. As you can see here, the 4 pillars are manufacturing physics, manufacturing systems, product development and design, and of course, business. And they're doing this work in the classroom, obviously with individual work, but many of these classes also have group projects. And so there's also an overarching theme of being able to work in groups, which we realize now is one of the fundamental skills that students need to learn to be successful in industry. And so taking that further, we then have these thesis projects that are done in groups inside a real world company. And these groups consist of 3 students. And they're usually, I say 3 students, there are some exceptions to that, and we'll talk about that a little bit later, perhaps in the Q&A. And the projects are, for the most part, full-time from during the summer, during the last summer of their 12 months. They start in September, they go through the following September. And so they're working full-time at these companies from the middle of May to middle of August. But they start working with the company earlier in the year, usually around February, and start meeting them once a week. And what's important here is that these are not just internships where they go in and then come back right out. They're actually working directly and very closely with a company supervisor and an MIT faculty advisor that has expertise in whatever the theme is of that project, whether it be design, production, or supply chain. And because it's an educational project, and because some of the intellectual property rules around that, in order to be able to have the companies participate fully and openly, the companies underwrite the full cost of the project, but in return, they have access to all the intellectual property that's developed as part of these projects. Now, as I mentioned, their groups are usually 3 students working in the company. There may be some cases for, in the particular situation of a company, where a team of 2 or a team of 4 may make sense, or separately, where instead of just finishing the project after 12 months, and that might be the case here with this pilot project in data science, they continue on to the following fall and finish in December of that year. So next, thank you. And so the idea of these pilot projects is exactly to test this idea out within a controlled context, right? And so we're doing it within the context of this program, starting, as Brian mentioned, in September, with the understanding that we're looking at testing out and implementing a core around computation, modeling, and simulation on top of what the students are learning very specifically about manufacturing. That's part of the advantage of doing this pilot with these students. They have the mechanical engineering base, as well as a very specific knowledge about the principles of manufacturing and the context of manufacturing and design. Okay, and so by doing this, we're able to test out how to implement it and get input not only from the companies, but also that input from our colleagues within the department. And so, as you can see here, part of our plan is to start convening companies to give us advice and guidance about what are the problems, what are the challenges and opportunities that we should be looking at that perhaps we haven't looked at yet, beyond what Brian has already mentioned, and also to inform us about, or inform the discussion about how we might expand this pilot into other programs within the department or perhaps even within the broader MIT context. Next slide. And this is just a summary of what I just said about the opportunities for partner companies. We're going to be having a couple of invitations in the end of July where you'll be able to learn more about this, as well as some of the details. But in general, we really are looking for opportunities to work with companies that are interested in testing these ideas out, on projects, challenges, and opportunities that are important to the company. These are not just for the benefit of our students, not just for the benefit of our research, but very importantly for the benefit of the company, because then we know the company is invested in success of the project, and that helps everybody. So with this, I might actually turn it over back to Brian and Dave to talk about the types of projects we're thinking about in this pilot.
Thanks, Jose. Let me just go also as well, just for information. I'm gonna go to the last slide here. I think Jose started to mention it, but so we'll have a number of emails that are going out for communication, but also if you click this link, I guess you can't click it, I can click it, but sort of data science manufacturing projects, there's an opportunity to sign up for our two-part discussion series that will start on the 23rd, so 2 weeks. Where we'll be having a roundtable discussion with companies, sort of further informing us, and certainly hoping to establish projects with many of you. But as Jose said, I had some bias in terms of the projects that I shared with you. They were in the manufacturing and design space, and certainly as a department, we're much broader than that. We're everything from thermal fluid sciences to optics to control and design. But what we're able to do within the context of the department, we have this 5-year program, or the 5th-year program, the MEng, that allows us to sort of, in the context of design and manufacturing, further amplify the phenomenal work that we've been doing as a department already in this degree program and in research. And so the nature of the projects are, for the MEng, fully broad in terms of design and manufacturing. But for the pilot set of projects, we want a heavier bias for a number of the projects, probably 4 or 5 of them, that are in machine learning, data science, so that we can really inform our further thinking evolution of the degree program that is the MEng in design and manufacturing, but also what we do as a department.
And I'll just mention one more thing about the advantage of doing this pilot within the context of the MEng. I already mentioned the important base of mechanical engineering, and then what the students are learning on advanced manufacturing and design and supply chain, that here's a new set of tools, a new set of concepts that can be immediately applied by these students in that context, because they don't have to pick up the context of manufacturing anymore. They already have that, and they're implementing it in the company. And so it helps us to start with this cohort, because we can start the projects right away and hit the ground running.
Yeah, let me just add a couple more words about both our experience with this already, and first, though, mention that the difference that you get when you have a Master of Engineering student working on these projects than others you might have worked with in the past. Having supervised bachelor's, master's, PhD, and MEng students throughout my career, the interesting thing is that because of this, the nature of our program, it's professionally oriented, it's career oriented, it's short term, we attract a different type of student that is very goal oriented and likes to get things done right away. And they're looking to get an experience in industry that will immediately translate into what they'll be able to do in their career. So we found that they can be amazingly productive in a short period of time, as well as working very well in teams. I think Jose and Brian mentioned that our curriculum is very project-based. So by the time they get to the company doing their project, they're very comfortable working in teams and may have worked in the same team before, same team of students. The second thing I'll mention is that this is not new. We actually have had organically a number of machine learning data science projects in recent years. Students working on video processing, on large data sets in continuous production lines, and working both with in warehouse systems, and inspection systems for warehouses. So a broad range of applications, and several of those have been in startups, and the students have actually, by the founder's own admission, had a significant impact on the progress of the company. So just to emphasize that we tell the students we expect them to accomplish something of value to the sponsoring company during that time in the project. So that's I would say that our batting average on that is extremely high.
And so maybe we'll conclude by emphasizing that the invitation here at the end of July for these sessions is an opportunity for us to hear from you, for you to participate in giving us guidance. And if you go to the website there, you can sign up to register for participating in these roundtable series. And we're very excited to hear your ideas, your guidance in general about what are the things we should be looking at, how we can improve this, both for the benefit of the students, but also for your companies.
So I know we're at the time where we do want to end. So I know there's some questions here. Many of them are very targeted, so I can answer them offline. But broadly, some of the students are asking about the opportunities for education in AI and machine learning, in using it in design and manufacturing, and certainly that's the heart of what we're trying to get to. Take your fundamental engineering understanding and amplify it with additional tools that are not that dissimilar from things you've learned, but we can do them bigger and better now with more data and more cost-effective compute. So I do hope you will join us. Please follow the link here and come to the roundtable. Irina, I think if you can pull up the last the exit slide as well, but I can just start to. We're going to take the summer off, the rest of the summer, in terms of the MECI Alliance seminar series. We have, as you can tell, a lot of other things going on to plan for the coming semester, for the fall. So again, this is our opportunity to engage with internal folks, external folks, our students, our alumni, company partners. So do drop us a line if, when we pick back up in September, you have recommendations for the types of things that you would like to hear. If you want to get on the mailing list, there's the other links. And with that, Dave, Jose, Irina, thank you very much for today. Your participants, thank you for your time, and hope to see you in a couple of weeks, and drop us a line to chat more. Thank you, and have a good day.